Okay, so as in the last video we have discussed about the dimension, or we have taken out the dimension of the potential difference. Alright, here you can see the dimension of the potential difference was ml2 t minus 3 a minus 1. And how did we get this dimension? By using the formula, and we know that potential difference is nothing but it is the dot product of electric field intensity and the displacement, which are both vector quantities, and we do have dot between these, right, where we got that electric field will be equal to force per unit charge. We have done nothing but we have substituted force per unit charge instead of this electric field here, right? So force per unit charge into displacement. We know that the unit of force is Newton, the unit of charge is coulomb, and the unit of displacement in meter. Now we know that Newton is equal to what? Newton is equal to ma, which means mass into acceleration, and mass into acceleration is equal to kg into meter per second square, and the dimension of force is mlt minus 2. Alright, so and we know that coulomb will be equal to what? 1 coulomb is equal to 1 ampere into 1 second. So we have just substituted this value here. So we know that now Newton dimension is ml2 t minus 2, and m means this is useful length. So here we have written length plus ampere into second. So ampere into second, when they'll gonna go up, they'll gonna have minus sign, right? So m l t minus 2 same, l same. When they both will go up, they both had negative sign, means a minus 1 t minus 1. Now we need to simplify it, right? So m same, l 2 l are here, so l square, of course we have 3t, and minus 2 minus 1 is minus 3, so t minus 3, of course a minus 1. So finally we got the dimension of potential difference, which was equal to ml2 t minus 3 a minus 1. In today's video we are going to see the relation between the electric potential and the electric intensity. So wait, let me write the topic here. Today we are going to discuss about the relation between electric potential and electric intensity, right? Electric intensity. Now for suppose here I have a charge, right? I have a charge here. This is, you can say, point charge or source charge. Here I have another charge as well, and that is q naught, of course, the test charge, or you can say unit positive charge. And here we have displacement. Let me highlight this first. Topic we have relation between the electric potential and the electric intensity. We know that we have taken two charges. Alright, now what's happening? The work done in moving test charge, this test charge from lower potential. We know that here the potential will be lower. It will be lower. Alright, and here the potential will of course be higher, or you can say it is positive terminal. And here we have what? Here we have negative terminal, right? So work done in moving this charge from lower potential to the higher potential against the electric field. We know that the electric field would be like this, but it is moving in this direction, so it is moving against the electric field. So work done in moving a test charge from lower potential, here we have lower potential, to the higher potential against the electric field. This is what we call the potential difference, right? So what we have done, let me guys make you consider this, right? This is very easy. So consider consider a test charge, or you can say unit positive charge, test charge q naught is placed, where it is placed, wait, it is placed at a point a, right? So let me suppose this is a point A, all right, to another point B. We have another point B. So let's suppose this is point B to another point B. Against the electric field, as I've already told you, right? Electric field. So the work is stored in this charge, work is stored in the q naught, work is stored in the unit positive charge, work is stored in the test charge. The work is stored in the charge in the form of electrostatic potential energy, in the form of electrostatic potential energy. This is a very important topic in terms of MCQs. Electrostatic potential energy, all right, potential energy, or you can say work done per unit charge against the electric intensity. That is also what we call the potential difference. All right, now we have considered this too. Now let me make this diagram again, because now we have written the definition and now I have made you guys consider, right? So now it would be easy. Now consider a test charge. We have considered a test charge here. Test charge is what? It is unit positive charge, is placed at a point B, which means this is a place and it is placed at a point B to another point B, which means it is going to a point which is B, alright, against the electric field. We know that there is the source charge, so it will gonna produce the electric field, wait, in this direction, right? But this charge is moving against the electric field, then the work is stored in this charge, and this is what we call the electrostatic potential energy, right? So we have considered two charges. One charge q naught is placed at a point B, and to another point A, it is moving against the electric field, then the work is stored in this charge, and that work is known as electrostatic potential energy. Now I hope I have made this very easy for you to understand. All right, so let me tell you guys formula of this again, so that it cannot create any confusion. Or you can say you know what, work done per unit charge against the electric field, as I've already told you this, right? Work done per unit charge against the electric field. This is work done per unit charge against the electric field, all right. This is also what we call the potential difference. All right, now we know that work is equal to what? Work is basically dot product of force and displacement. These both are vector quantities. When we remove this dot, we'll have function cos theta, and that would gonna show us the angle between the force and the displacement. All right, now substituting this force dot d in this first equation, all right, so let's substitute this. del V is equal to force dot displacement, or you can say small displacement, right? Force per small not per into small displacement and upon a force charge. Now, as we have already discussed the electric field was the ratio of the force per unit charge. I need to have a value of this force, so of course this q naught is dividing here. When it will go there, it will be multiplied. So of course finally we have got F is equal to E q naught. So let's put this instead of this formula, right? So del V is equal to instead of F, I'm going to write EQ dot del R upon Q naught, right? This Q naught cancel, and of course in the end what we have gotten, it is the dot product of electric field intensity and the displacement. In the answer we're going to have scalar quantity, and that is what we call the potential difference, right? So this was all for today. In today's video we have discussed about the relation between the electric potential and the electric intensity, and of course we have again, this is the second time we have derived the formula for the potential difference. In the next video we're gonna see the magnitude of it, and of course we will be I'll introduce you to a potential gradient.